Alright, Assalamualaikum. Welcome back, guys. Today, we have, we move another topics. So we have got another stoichiometry like question right now. Let's explore. So, now we are moving on to another topic, which means stoichiometry, especially the previous one, kind of like the basic of stoichiometry. So, like, try to find out the moles and then what else? Like moles and then percent composition and like the empirical and then what's the next one is, yeah, mostly about that one. So there is no reaction happen for the previous uh problems or previous topics. Now we have another topic, but it cover more. Okay, it covers more. It will cover more about balancing chemical equation. Looks like try to find the smallest number coefficient and then other stuff. Okay, so now we gonna do for the first question. The question is about what are the smallest whole number coefficient for each substance respectively in chemical equation when balanced. Okay, and then we have options such as this one. Okay, so now our goal is to conserve atoms. Okay, what goes in must come out. Okay, we will balance silver, iodine, sodium, and sulfur over here. Okay, so let's break down step by step. Okay, now we have this one. Okay, this is the equation of this is the equation that unbalanced. We need to balance this one. Okay, now count atom and balance one element at a time. Okay, now we try to balance for silver first. Okay, Ag or silver on the left, Ag is AgL and then 1 Ag per molecule. On the right, Ag has 2, okay, atom. So we need Ag to supply to Ag atom over here. Okay, so now silver is both are equal. And then now we are moving on to another part, which is sodium. Sodium here is 2. And then over here, we have to put in 2 as well. Okay. Now, check iodine again. Iodine in the first one. Okay, iodine in the first one over here is 2. Okay. So, we need to get this thing same as well for right side. So, now the right side is also same. So, both are correct. Okay, iodine and then silver and then sodium. How about the Ag2 is same? How about the S? S or sulfur is just 1, okay? And then sulfur also 1, okay? So now all of them already balanced, okay? So the correct answer should be B. Okay, so the final balance is kind of like this one. Just a quick recap that we have to double check the subscript. Okay, we need to double check for each subscript. Always finish by checking that all elements are balanced. Okay, after, so the first part that you have to uh balance, you have to balance so one element one by one. Okay, and then kind of like trial and error, like you plug in for this number and then plug another number, and then sometime you have to go back again to make sure both are balanced. Okay, so now move on to let's roll on another question. This is one about balancing equation again, and then how many like natrium chloride. Okay, what is the coefficient for natrium chloride or sodium chloride when the reaction below is balanced with the smallest whole number coefficient? Okay, so in this question we are working on, we are working with an ionic exchange reaction. Okay, two compounds swap their cation and anions. Okay, so over here CaCl2, okay, CaCl2 will give let me break down step by step. Okay, let me break down step by step. CaCl2 will be Ca2 plus Cl minus 2Cl minus. Okay, and then Na3PO4, it will be 3Na plus, and then PO4 3 minus. Okay, so now let's break down, let's take a look at another one. The step by step balancing, how we understand we can solve this problem. Okay, let's take a look at product size first, since the polyatomic ion gives us clue over here. So this one is polyatomic ions. Okay, polyatomic ions. So over here, okay, you can start from polyatomic. Okay, because this one is kind of like a clue for us. Okay, Pa4 and then Pa4 2. So to make it balance, we have trying use plug like 2 over here. Okay, try to plug 2 over here. And then now we are moving on to like product, another product side again. So over here, Na is kind of like 6. So if we are putting 6 over here, let's try it. 6Na. Okay, 6Na. All right, because this one 2, this is 3. So Na is kind of like 6. And then now Cl is already has 6. And then we can put in over here 3, for example. Because Ca3 over here is already 3, so we don't need to put in something in front of this this element, this molecule, so we can put in 1. Okay, it looks like it's already good for balancing this one. So the answer is 3 CaCl2, 2 in Na3PO4, 1 Ca3, and so on. And then the answer should be what? This one. So what is the coefficient? The question is about the coefficient. The coefficient here is for NaCl when the reaction below is balanced with the smallest whole number of coefficient. So we already got the smallest number because we already got 1 over here. So we don't have any kind of like we need to divide it what by what, no, over like 1 what over what, no, we already has the smallest number over here. So what's the answer? Remember that the Na over here is 6. The total Na is 6. So the answer is should be 6, not 2, not 3, not 1. Okay, so when balancing reaction with polyatomic, keep them together if they appear unchanged on both sides. Match them. So trying to start from the polyatomic first, and because it give us clue to start from there, and then balance one by one. And then remember that we need to understand over here like the coefficient of Na. Okay, the coefficient of Na. All right, and then let's go through another question again. So for you guys, I have a tip for this one. So just doing trial and error, but keep in mind that we need to arrange one by one. So focus on one side and then moving to another side. I mean, from the product, start from product or start from the reactant. After the reactant is already balanced, you can go to product. Okay, don't like go over like randomly. Okay, go over randomly. So it's kind of like it will make us much more it will make us like confused and then getting much more complicated to, I mean, we need to solve the problem quickly, but like if you doing many things, it will be worse. Okay, so again we want to move to another part. Determine the number of mole carbon dioxide formed when 2.5 mole ethanol undergoes combustion in excess oxygen. Okay, so now we have kind of like this one. Okay, determine number and then blah 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 blah. The equation is kind of this, right? The equation of the formula, I mean of the reaction, kind of like this. And then we are asked about determine the number of mole carbon dioxide form. Okay, number of mole carbon dioxide from when 2.5 ethanol undergoes under combustion in excess oxygen. How to do that? How to do that? So 2.5 ethanol. Okay, this is small. Okay, this is small. So this reaction is excess in oxygen. So no limiting reagent worries there, because this one is like excess oxygen, no limiting reaction. Okay, so now we can do something over here. So if we take a look at the information, is this one is 2.5, right? 2.5 mole. And then you know that over here from this information we can understand, because this one is 1 coefficient, the coefficient of this one is 1. Okay, from the ethanol. And then for CO2 is 2. So how to get the mole of the CO2? Just 2.5 times 2. So it should be 5 mole. It's very, very easy. And then you can solve it like just one, like maybe 2 seconds or 5 seconds, as long as you understand the equation. Okay, it's very, very easy. All right. Now moving on to another part again. Okay, just quick tip, always look at the mole ratio from the balance equation. Look at the mole ratio. If ethanol again, if ethanol give us 2 CO2, yeah, if 1 ethanol give 2 CO2, then 2.5 ethanol gives double that. Okay, it will doubles that. Okay, so what is the mass in gram ammonia necessary to produce 0.340 mole NO in the presence excess oxygen? No limiting reaction. No limiting reagent. Okay, now the mass, the question is about mass in ammonia to produce 0.340. So now based on the equation, we need to put in over here 0.340 mole. Okay, and then let's take a look at the ammonia itself. Because the coefficient number is same over here, 4 and 4, so we can determine here it's same, 0.340 mole. And then now we need to take a look at the gram of ammonia itself. How to get gram is very easy. Just mole gram per molar molar mass. Okay, molar mass. So it should be, for to getting gram, our mass, it should be mole 0.340 times mr is 17.03. So this is the answer of the equation. So it's kind of like around 5.79 gram NH3. So the answer should be C. Okay, and then let's move on to another part again. Right, and then this is just for study question, guys, not the real question. Okay, we have kind of like 30 question. This we haven't start yet for the practice exam. So let's see. Okay, and then now we are moving on moving on another question, but this question is talking about limiting reactant and then mass yield. Okay, mass yield. Okay, the first one, what is the theoretical yield of NO that can be produced from the reaction? 3.5 mol NH3 and then 4.0102. Now we have to know the limiting reagent. Okay, limiting reagent or reactant. Okay, just put in over here to make it easier for us to calculate one by one. 4NO, 6H2O. Put in the NH3 3.5 mol, and then put in the O2 is 4.01. Okay, which one okay that has smaller ratio? Which one that has smaller ratio? Okay, for the first one, for the NH3, okay, for NH3, so NH3, so we have 4 and then 3.5. So now we need to understand one NH3, so divided over 4, so 0.867. How about O2? O2 is 5 divided over oh no, 4. Yes, 4, right? 4 over 5, so 0.802. So the smaller one is O2. Okay, the smaller one is O2, which mean O2 will be uh O2 will be what? O2 will be used or will be complete first. Okay, it will be complete first, right? So if we put it over here like I mentioned before, so it's kind of like over, no way. So H3, so probably we can do hmm O2 is limiting reactant. Yes, limiting reactant. So how to get that one? I just wondering if we can use something different over here. I mean, not using kind of like too complicated, but let's see if we can do. So the question is, what is the theoretical yield of NO? Theoretical yield of NO. NO. So limiting reactant is O. Okay, so 4NO. 4NO. So this one is 3.5. Okay. And then um it will be complete first for O2. So let me think first. So oh, okay, I understand. Now we use this one to get the comparison, okay, because this one is limiting reactant. Okay, so now we just take a look at this one, 4NO, okay, 4NO, okay. So because this one is limiting reactant, so we will use this comparison. So if 5 is 4.01, how about if 4? Okay, did you get my point? So is 5 is 4.01. How about like if this one is 4? Okay, how about like if this one is 4? So to solve this problem is very easy. Just 5x 4.01 times 4. Okay, so let's take a look at the answer. So I use the calculator for my phone. 4.01 times 4. Oops. 401 times 4 divided by 5. So the answer of x is 3.20x. So 3.20x. Okay, so this one it should be this one A. Yep. Okay, that's good. So yeah, we need remember, just quick recap for here, that we have to understand first which one that limiting reactant, and then using the mole of limiting reactant we can do comparison between limiting reactant and then the molecule that the molecule will be, the molecule that we need to find out. Okay, so probably those are a good, this question is very good example, because we start from the very very simple first. Okay, very simple. All right, so now let's move on to another part. What is the mass in gram of TiO2 when the ICL are react with the 0.0 blah blah blah. Okay, this is the question. What is the mass of TiO2? The mass of this one. Okay, now again we need to determine for the limiting reactant. Okay, so let's start from TiCl4. Okay, TiCl4. So just quick, what we can do it very quick. TiCl4 divided by 0.476 per what, TiCl4 is 189.7, and then 0.0501 because of S2, right? Because of S2. No, just like this way, and then 18.02, and then this one is 0.00278, and then how about this one, 0.00251. But the reaction needs 2 mole H2O. Okay, so H2O is time 2. Okay, so it will be 0.00502. Okay, so now when we are looking at the answer over here, okay, so this is the thing that we require. Okay, because it has two over here, we require around 0.00502, but it's not enough H2O. So what we're gonna use here is H2O is limiting reactant. Okay, H2O is limiting reactant because it's H2O not enough H2O. Okay, but the reaction needs 2 mole H2O per 1 mole TiCl4. Okay, So I repeat it again. Okay, to understand this problem, we need to find out like the mole of one molecules. Okay, mole of one molecules. Okay, so in this case, H2O consists of two molecules. Okay, right, and then uh and then again, wait again, 251. Okay, the reaction over here. Okay, uh the reaction needs 2 mole H2O per 1 mole TiCl4. Okay, and however, H2O available is just this one. Okay, okay, the require of H2O is around this one. Okay, this is the require H2O needed. Okay, require H2O. Okay, so H2O will be a limiting reactant. So how to solve the problem? From the reaction to mole H2O to 1 mole TiO2. Okay, so we already get the H2O 0.0278. Sorry, and then we need to divide it by 2, right? Because TiO2 is just 1. So we ended up getting like 0.00139, and then now convert it into gram. So this is small, right? So now is times to 79.88 of what? This one is the IO2 from here. So the answer of TiO2 in gram is 0.11 gram. Okay, like this. Okay, so just recap that no theoretical yield, and then O2 is limiting reactant, and then for the previous one, okay, the previous question, and then the last question is TiO2 from TiCl plus H2O. H2O is limiting reactant. Okay, so please keep in mind that we need to find out the limiting reactant first. Okay, how to get that one? Just look at which one that like finish first. Okay, will be finish or will be complete first. All right, so now move on to another part or the last question for the study question. Okay, now we have another question, but this question is kind of like it's still same, yeah. Balance reaction, and then an initial we need to read the question first. An initial reaction mixture of N2 and H2 is shown to the right, okay, over here. Which representation shows what will be present after the reaction is complete? Okay, after the reaction is complete. Okay, now we will see like how many N2 and then how many H2 and then how many NH3. Okay, which representation what will be present after the reaction? Okay, now we're gonna calculate one by one, count one by one. 1, 2, 3, 4, 5, 6, 7, 8. So H2 is 6. Okay, 1, 2, 3, 4, 5, 6. As well as for N2, it's also 6. So now, which one that has the smallest ratio? It will be the H2, right? It will be H2. So now, how to determine NH3? As you can see, we can use like if 3 is 6, how about 2? How about 2? Okay, so 12 and then 3 eggs. So egg, it will be 4. Okay, and H3 will be 4. Okay, will be 4. And then let's see which one that contains 4 and H3. 1, 2, 3, 4. Okay, just save it first. 1, 2. We eliminate this one. 1, 2, 3, 4, 5. We eliminate. Okay, so the answer should be A. Okay, the answer should be A because of what? Because like I mentioned, we need to determine the limiting reactant first. Okay, all right. And then we move on to real question right now. Okay, now we move on to the real question. Okay, and then let's take a look at and then let's answer one by one. Okay, the limiting reagent for a given reaction can be recognized because it is reagent that this is the concept. Okay, because this reagent that has the smallest coefficient in the balance equal for the equation for the reaction. Okay, the answer will be no. Okay, why? Because it's kind of like not this one. Okay, the limiting region runs out first. This is the key. The definition of limiting region is runs out or complete first. Okay, runs out first. Okay, and then it's not about mass or coefficient. Okay, it's not about mass or coefficient. Remember, it's about how far each reactant can go based on mole ratios. Okay, it's not about what? Not about mass and coefficient. Okay, and then it tell us like how far the reactant okay goes based on blah blah blah. Okay, based on mole ratios. Okay, so because it has the smallest coefficient, no, it doesn't has any correlation with the coefficient. As the smallest mass, no, there is no correlation with the mass as well. And that is present in the smaller quantity. Okay, so option C sounds tempting. Okay, sounds tempting. Sounds like it looks like makes sense, right? It looks like make sense because what sounds tempting, sounds good, right? Because the smaller quantity, but it's not just who has fewer moles, but which one that use up first. Okay, which one that use up first. Okay, right? It's not just who has fewer moles, but who will be used up first according to balance equation. So tips: always use mole to mole comparison from the balance to find the limiting reagent. But however, Don't just pick which one that's smallest one, but uh the most precise I think is will be used up first. Okay, the answer should be D. Again, okay, again, we need to remember the concept. All right, what are the coefficient for each substance respectively in the chemical reaction when balanced? Okay, like I mentioned, you can do we can do for the like this one just like getting trial and error, but we need to take a look at step by step, one by one. Okay, for carbon has 7. Okay, over here it has 7, so we can on the right is just 1, so we can put in 7 over here, just trying. Okay, just trying, and then we put in over here, it might be 1. Okay, and then you can take a look at from the option, it looks like D probably. The option D sounds tempting as well. Okay, just take a look at more. And then how about the H2O? Okay, in the left side, H2O is 14. Okay, H2O is for 14. So we need to put it over here probably around 7. And then remember, for the like diatomic atom like O2 over here, we can do it in the least time. Okay, in the least time, I mean in the end of when we want to do balancing. Okay, because O2 is much more easier, doesn't have any correlation with others. Okay, so and then now we need to find out for how many O2. Okay, O2 in the right in the right side is 14, and then this is 7, so the total is 21. And then we already have 2 over here, so 21 minus 2, it will be 19. Okay, it will be 19. Okay, it will be, oh no, it will be not 19, it should be what? Oh, we already have O2, so 19. 19, if we divide it by O2, which mean we will getting ended up like 19 divided by 2, like which is 9.5, right? 9.5. Okay, 9.5. Because we looks impossible. I mean, if we getting ended up like 9.5, multiply this equation by 2. Okay, we can multiply coefficient by 2 to eliminate the fraction. Okay, because looks impossible if we have fraction in the chemical equation. So just times 2, we getting ended up like 2C7H14O2 plus 9.5 times 2, which means 19 O2, and then 7 would be 14 CO2 plus 7, and then 14 again H2O. So the answer, it will be B. Okay, that's good. All right, what are the smallest whole number coefficient for a substance in the chemical reaction when balanced? Now the smallest one, the smallest coefficient for each substance. Okay, now the same thing, because we need to take a look at one by one first. Okay, NaCl, NaPr, and SlCl2, NaCl, and Pr2. Okay, so now which one first? Which one first we need to take a look at? Okay, so this is a single replacement reaction. Cl2 displace Pr minus. So the tip is here. Okay, watch for diatomic molecule like Cl2 and Pr2. They always come in pairs when alone. Okay, they will come in pairs when alone. Okay, so now start with 2NaPr first. 2NaPr, because we want to get this one Pr2, and then we Pr2 over here. Okay, so now we have 2Na, so we put in over here Na. And then how about this one? We have 2Cl in the right side, and then just put in 1. So the answer, it should be 2, 1, 2, 1. 2, 1, 2, 1. So it will be C for the answer. That's great. It's pretty easy, right? Okay. And then now we move on to another part again. So hopefully I can like finish 30 question directly. Okay, when this equation is balanced with the smallest set whole number, what is the coefficient for n2? Okay, what is the coefficient? When the equation is balanced with the smallest set of whole number, what is the coefficient for n2? It's pretty easy. You just need to much more carefully, because now not only diatomic atom, but it's kind of like yeah, still it's still pretty easy, right? It's still pretty easy. Okay, n2 over here and then over here. Okay, h4, h4. So if this one is 4, we would be have the small amount if we put it over here 2. Okay, if we put it over here 2, so the number of hydrogen it should becoming same. And then how about the oxygen? Oxygen over here is 2. Okay, oxygen over here is 2. However, in this part is 4. So to get 2, we will be good if we put in like fraction half. Okay, fraction half. And then now how about the n2? Over here we have 1, and then over here we have 2. So if it will be nice if put in this one is 1. So and then for this part we would have 3.2. Okay, and then we wanna do the multiply by like multiply by 2. So it will be 2n2h4 plus 1n2o4, and then it will be 3n2 and then 4h2o. Okay, what's the coefficient of n2 for at the end? It will be, the answer is 3. Okay, it's very I mean, it's still like manageable. Okay, for the answer is still manageable, no issue at all. Okay, and then yeah, we gonna do for the number 5. What is the coefficient for Z and O when the reaction is balanced with the smallest whole number coefficient? Still same process, still same way to solve that problem. Okay, how many what for diatomic? We would start for the last one, so it's already okay. If I put in over here is 1, and then I put in over here is 1, so the amount of the amount of O is should be 3. So how to do it is like 3.2. Okay, 3.2, and then we put it over here is 1, and then we make it balance like 2ZNS plus 3O2, and then 2ZNO, and then 2SO2. ZNO it should be number 5, it should be B. Okay, so it's very easy for the answer. It's kind of like when I was young to solve this problem. Yeah, overall it's pretty nice until now. Yeah, there is no issue for the to answer the question. So let's move on to another part. What are the smallest whole number coefficients for each substance in the chemical reaction when balanced? Okay, now this question are us about the smallest again. Okay, so now let's take a look at first for CO2. C is 1. How about H? H over here is 4. Okay, over here is 4. So it will be good if we put in here is 2, right? And then now how about the oxygen? oxygen here is 2, and then this one is 2, so we put it over here 2 again. And how about the carbon here is 1, and then this one also 1. So 1 2 1 2. It will be good if we like choose for A option. Okay, it looks good now. So the answer number 6, it will be A. That's nice. And then number 7. How many moles of iron are necessary to react completely with 1.75 mole of oxygen gas? Okay, so 3O2 plus 4 iron, and then 2Fe2O3. So this one is 1.75. And then how many moles iron are necessary to react completely? Completely. Okay. So how to get this one? So kind of like if 3 is 1.75, how about the 4? Just kind of like this way, 3x 1.75. 1.75. So 1.75 times 4 over 3. 2.33. So the x is 2.33. So it will be good. 2.33. So the answer should be C. Number 7 is C. Okay, number 7 is C. And then again, for this question, what mass of the NO2 is formed by the complete reaction of 2 mole O3 with excess NO? Okay, O3 plus NO becoming O2 plus NO2. Okay, so complete reaction. So the excess, okay, what mass of NO2? NO2. So the equation is about this one. Is formed by the complete reaction of 2 mole O3. 2 mole O3. And then the excess one is NO2. So there is no limiting reaction over here. So if this one is 2 mole, it's already balanced, right? It's already balanced for yes, it is. So it will be 2 mole as well, okay, for NO2. So NO2 like gram, mr, and then mole. So to get gram over here is 2 mole, okay, times 46 gram per mole. So it will be, the answer is 92. Okay, so the answer is should be C. Should be C. Number 8 is should be C. Okay, how many moles Pa3N2 are necessary to react completely 1.5 mole of water? Okay, Pa3Na2, 6H2O, 3PaOH2, 2NH3. How many moles of Pa3N2? Okay, now water is 1.5 mole. Okay, water is 1.5 mole. Okay, remember this one is very important. React completely. So if 6 is 1.5, how about if 1? How about if 1? So the answer is should be 1.5, and then 6x. So the x, it will be 1.5 over 6. Okay, 1.5 over 6. The answer is should be 0.225. 0.25. Number 9 is A. Okay, it's very easy. Okay, and then number 10. How many moles of water are necessary to react completely with 8 mole PCl, what it is, PCl5. Okay, so PCl5 plus 4H2O coming H3PO4 5HCl. So this one is 8 mole. And then how many moles of water to react completely? Again, react completely. If one is 8, how about if 4? Okay, how about if 4? So X would be 32. So the answer will be D. Alright, so I think I don't have much more energy. I'm feeling sleepy right now. So we're gonna do again for the remaining question, the left question. So kind of like 20 question again, but I'm pretty sure I can do it maybe like 6 hours later. So we can like getting rest right now, take a rest, and then thank you for joining me. I mean, thank you for joining us and then for watching this video. Hopefully what I explain is pretty clear. If you are having any issue for your, I mean, for the to solve the problem, please let me know, just comment below, and then okay, see ya.